Hi, and welcome to our presentation.
Hello there, I'm Zachariah Kohi. I will start off by presenting our project. This project consists on using a model to see how a virus should impact the world throughout time. To do so, we will be using an SIR model that we are going to apply to multiple countries and the world. This SIR model consists of three variables: S for susceptible people, I for infected people, and last but not least, R as the recovery rate. So the purpose of this model is to match as well as possible real data for 2020 for the spread and recovery rate of the COVID-19 virus. Background information on COVID-19. COVID-19 is a newly discovered infectious coronavirus disease. It was discovered back in December 2019 in Wuhan, China. Ever since then, the virus has spread all over the world, creating a world crisis. To fight this pandemic, the world population had to isolate itself and countries had to lock their frontiers. All of this had to be done because of how highly contagious this disease is. Also due to the fact that variants have been emerging all around the world, which is only making things worse. This is why specialists have to make predictions on the virus's spread to inform the population. The equation used in this model to calculate the future spread of COVID-19 is S of t equals S0 times exponential of negative R0 times R1 minus R0, all of that divided by n. With our variables being S of t for the number of susceptible individuals as a function of time, R of t for the number of individuals that have been removed as a function of time, and S0 and R of 0 being the initial values for respectively the number of susceptible subjects and the number of removed subjects.
Hello, I'm Max Denemy, and in this section, I will be discussing our base model results. Let's get started. On the y-axis, we can see new cases. This shows cases in the thousands. This is helpful to show the impact better, and as you can see, within a short amount of days, it creeps up very high very quickly. The blue curve represents our projections and the red circles represent the real-world data. As we can see, both China and South Korea have similar transmission and recovery rates, yet the projections look very different. This can be attributed to a few different reasons, like population or how much testing they've been doing. The graph on the left shows the global data with the previous month, and the graph on the right shows the global data and a month after the start of the outbreak. The results of both are highly sensitive to both transmission rates and recovery rates. This is because of the nature of the transmission rate being potentially exponential. Unfortunately, we cannot yet determine the true nature of the curve based on our base model, but we can look and see the patterns as they develop, showing how reliable our model is. Many things can change how our parameters function, like vaccines and quarantine, to affect the transmission and recovery rates. A simplistic model is necessary, especially in scenarios with many variables that cannot be measured, such as those infected yet never tested. By using a model that is simple, we can look at the data in many different ways and discover many different things we did not know. It would be quite easy to tamper with or abuse a model like this by changing parameters or variables or even increments to make the data look however someone would want. So we must always be careful.
This is the analysis. The assumptions built into our model and equations are that the infected people start out by spiking up and peaking right after the pandemic starts, then start regressing afterward. The regression continues until it gets closer to zero. Our models and their equations also assume that the susceptible people start out high and then drop to zero a few days after. We also assume that lowering the transmission rate will cause the infected people to become lower than the susceptible people. The definition of lumped parameter is multiple variables have to be combined into one in order to make a more simple variable. This makes modeling easier. Real-world variables in our models that are lumped are transmission and recovery. For transmission, we lump together people following social distancing and access to paid time off. Paid time off is good for preventing the virus since it gives an employee a chance to be away from sick people so they don't get the virus. Practicing social distancing has a large impact since it prevents the virus from going into another person as you're further away from the contaminated person. Real-world variables that are lumped into recovery are age, meds, and access to a doctor. Age can be a factor because elderly people can be more affected. Meds can be a factor because they can reduce or increase the spread of the virus depending on different circumstances. If we separate these lump parameters into different variables, the challenge would be splitting up transmission and recovery and still having a good model that works with a bunch of variables that we'd have to get data for. Also, knowing how they interact would be a challenge because we'd have to add more to the formula to understand those factors.
Accurate predictions for the outbreak. In order to get the best model possible and fit the curves with the data points, a few important steps were taken. Started with the estimates. Using Italy's transmission and recovery rate as basis, we transferred that number over to the other countries. We would tweak the start scale to try and match it up with the initial numbers, and then, once those seemed accurate, it was essentially a rough guessing game. Starting with broad strokes, we increased the whole number, both the transmission and recovery rate, until peaks and curves seemed to match the data horizontally. After that, we would tweak the start scale and the decimal difference between the transmission and recovery rate until the curve matched as best as possible. While there may have been more methodical approaches, this one worked, for I am very lucky. These were the results. As we can see, Western countries, such as Italy and the United States of America, follow the curve very well, while China follows it after the first 10 days or so. South Korea, however, refuses to follow the model in any way. While this does show a possibility of Western nations being more resistant to the virus, resulting in a lower transmission rate, I believe this is more a result of lack of population density. The outbreak in China peaked incredibly quickly because it was an incredibly dense population center. Meanwhile, Italy and the US don't have as many dense cities. This speed of transmission is likely why China is unable to follow the beginning of the SIR model. It hit so fast that they were unaware it was a pandemic until after the numbers were already very high. South Korea, however, is a different beast entirely, as it doesn't follow the SIR model in any good sense. While there are many possible reasons for this, such as a doomsday cult or high population density, I believe it is because of the SIR model's assumption that no one can catch the disease after recovery. This is an easy explanation for case spikes, though on a global level, it still doesn't seem to match very well. Both of these models show the global number of cases, but the one on the right includes a month prior to the one on the left. Including this prior month, we see the number of cases take a small dip followed by a sudden spike. This dip can't be made in the SIR model because it isn't designed for cases to decrease until after the peak. This shows the flaw in the SIR model and ultimately that it shouldn't be trusted as a perfect long-term tool. The SIR model predicts a total of 594,800 cases in the US, only 0.18% of the population. This number is nowhere close to the actual number of cases through the pandemic, with the actual count rising above 30 million, clearly showing that it can't be trusted. One way to improve the data might be to separate the recovered by living and dead, because the living can be reinfected. Another method to take into account is the population density, as that would likely help determine how fast the disease is spreading.
Thank you for watching our presentation. We hope you've learned something.